Let me ask you something a little mind-bending. Is the world you see around you real only because you're looking at it? Or are there an infinite number of other worlds just like this one, branching off from ours every single moment? This, right here, is quantum's great divide, and today we're diving straight into the heart of it. You know, at the core of all of quantum mechanics, there's this one, completely baffling question. For almost 100 years now, the smartest people on the planet have been locked in this fierce debate over whether the simple act of looking at something fundamentally changes what that something is. It's a puzzle that we call the measurement problem. Here's the real head-scratcher. Quantum theory seems to have two sets of rules that just completely contradict each other. It's this sort of dynamical dualism. See, when we're not looking, a quantum system just evolves smoothly, predictably, everything's humming along. But the instant we measure it, everything changes. It suddenly, randomly, and totally unpredictably jumps into a single, definite state. So how on earth can both of these things be true at the same time?
All right, so let's break down these rules. Rule number one, you've probably heard of it, the famous Schrödinger equation. The best way to think about it is as the law of the land for the quantum world when it's just left alone, in peace. It describes this beautiful, continuous wave of possibilities, where a particle can be in many places or many states all at once.
And then you've got rule number two, wave function collapse. And this one, it's a violent interruption. The moment we try to measure anything, that graceful wave of possibilities just collapses. It slams down into one single concrete reality. The particle is now here and only here. That smooth, predictable evolution gets shattered, and a random outcome takes its place.
So, this is the measurement problem in a nutshell. Why does nature suddenly switch rules? And what even counts as a measurement? Is it a Geiger counter clicking? Is it a human eye seeing something? A conscious mind? The theory gives us absolutely no clear answer. And it's this vagueness that sparked one of the greatest scientific debates in all of history. And you know who was the first great challenger who absolutely could not stand this idea? Well, of course, it was Albert Einstein. He was just deeply, fundamentally troubled by the idea that reality was based on chance, and that it somehow depended on us, the observers. He was convinced that quantum theory had to be missing something big. I mean, this battle just raged for years. You had the legendary Solvay conferences, where Einstein would cook up these brilliant thought experiments to try and find a flaw in the theory. And Niels Bohr, who was the theory's main defender, would cleverly find a way to refute them, one by one. But then, in 1935, Einstein completely changed his strategy. He stopped trying to prove that quantum mechanics was wrong, and instead started arguing that it was just incomplete.
At the very heart of Einstein's new argument was this core philosophical belief, something he called a criterion of reality. To put it simply, he said, look, if you can know something about a particle without ever touching or disturbing it, then that something has to be a real pre-existing property. It couldn't just pop into existence the moment you look at it.
And the weapon Einstein chose to prove his point was a phenomenon so bizarre he famously called it spooky action at a distance. Today, we just call it entanglement. It's this really strange quantum connection where two particles become linked, and whatever happens to one of them instantly, and I mean instantly, affects the other, even if they're on opposite sides of the galaxy. So here's how Einstein's logic worked. Imagine you have two entangled particles. If you measure the spin of particle A, you instantly know the spin of particle B, without ever going near it. So according to his criterion of reality, that means the spin of particle B must have been a real, definite thing all along. And if that's true, then quantum mechanics, which says the spin was undecided until you measured it, must be an incomplete theory. It's missing something.
But Niels Bohr, he had a counterargument, and it was just as radical and maybe even more powerful. His view, which we now call the Copenhagen interpretation, would pretty much become the standard orthodox way of thinking about quantum mechanics for decades.
Bohr's central idea was something he called complementarity. He argued that things like being a wave or being a particle aren't fixed properties that an electron has. They're more like different faces that it can show you, depending entirely on the kind of experiment you decide to build. The observer isn't some separate bystander. Your choices are part of the phenomenon itself. So for Bohr, when Einstein said, without in any way disturbing a system, that phrase was the entire problem. The disturbance he was talking about isn't a physical nudge. It's that by choosing to measure, say, the position of one particle, you fundamentally change the conditions that define reality for its entangled twin, even if it's light years away. You don't discover reality, you create it by asking the question.
For decades, Copenhagen was really the only game in town. But then, in the 1950s, a young grad student named Hugh Everett came along and proposed something so breathtakingly bold, it's still hard to wrap your head around today. He basically solved the measurement problem by taking the math more seriously than anyone ever had.
This new idea is called the many-worlds interpretation, and it makes an absolutely incredible claim that violent collapse of the wave function, rule number 2, it never happens. It's a fiction, an illusion. According to many worlds, the smooth, predictable evolution of the Schrödinger equation is the only rule there is, period.
So if there's no collapse, what happens when you measure something? Well, according to many worlds, you don't force the particle to make a choice. Instead, you become part of the quantum system. You get entangled with it. And then the entire universe, including you, splits. In one reality, you measure the particle's spin as up. And in a completely separate parallel universe, an exact copy of you measures the spin as down. Every possible outcome becomes real, just each in its own universe.
Okay, so we have our two heavyweight contenders trying to explain the very nature of reality. One says reality is created by our observations and involves some mysterious collapse. The other says all possibilities are real and the universe is constantly branching into this multiverse. So let's put them head to head.
Let's really compare them. On measurement, Copenhagen says the wave function collapses. Many worlds says the universe branches. On reality, Copenhagen says it's created when you look. Many worlds says it exists independently of you. But here's the real surprise, the math. You'd think many worlds would be more complicated, but it's actually simpler. It only uses the Schrödinger equation. Copenhagen has to tack on this extra mysterious rule of collapse. The trade-offs are purely philosophical. Do you prefer a theory that's vague or one that's just extravagant?
The biggest knock against many worlds is what philosophers call a bloated ontology, which is just a fancy way of saying it seems completely, absurdly wasteful. To get rid of one little inconvenient collapse, you have to believe in a literal, infinite number of unobservable parallel universes, filled with copies of you living out every possible decision. For a lot of physicists, that's just too high a price to pay.
But hold on. The Copenhagen interpretation has its own huge flaw, this thing called the Heisenberg cut. It needs this fuzzy, arbitrary, imaginary line between the tiny quantum world, where all these weird rules apply, and our big, classical world, where they don't. But where is that line? How many atoms does it take for something to cross over? The theory doesn't say. It's fundamentally ill-defined.
Now, you might be thinking, okay, this is all just some weird, dusty, philosophical argument from 100 years ago, but you'd be totally wrong. This debate about the foundations of quantum mechanics is more active and more urgent today than it has ever been. And that's largely because we're now trying to build quantum computers, machines that force us to control the quantum world without collapsing it. We have to confront these questions head-on.
And we're not just doing thought experiments anymore. We have incredibly precise Bell tests that have now definitively slammed the door on Einstein's simple, local version of reality. And at the same time, you have these radical new theories popping up. There's one called cubism, for instance, that suggests the wave function isn't a real physical thing at all, but just a mathematical tool that represents our personal beliefs about a system. The ground is constantly shifting under our feet.
And that brings us right back to where we started, to quantum's great divide. Does our act of asking a question conjure a single reality out of a fog of pure possibility? Or does it simply tell us which branch of an infinite, sprawling multiverse we happen to be living on? We don't have the final answer yet, but the search for it is pushing us to the absolute limits of what we know about existence itself.